again. So, all right. I got some things to hand back to you, ladies and gentlemen. If you would take and pull out your computers, open them up to your EISN, a new one for Unit 6, ladies and gentlemen, because that is where we are at right now. All right. Yes, sir, Alicia. I'll bring you on in just a second, sir. Yes, Wendy. Come up and take this one. I will go grab his in a minute. All right, ladies and gentlemen. So, Landon. Parker. Thank you, sir. Morgan. Arnold. Jesus. Wendy. Ethan. Simon. Zell. All right. Madison. Madison, put your phone in your headphones, please. Kayla. Elsa. Daniel. Claire. Paula. Lydia. Shannon. Linda. All right, so take a look at your test, ladies and gentlemen. I will put the answers up in just a second. First thing you should always do when you get a test back from me, count up the points on each page. Make sure they match the total that I wrote down in the corner. Add up the totals in the corner. Make sure they have the total that I have on the front. Otherwise, I didn't give you all your points. Okay, we have two versions of the test again, ladies and gentlemen. We have version A and version B. If you have version A, ladies and gentlemen, it is the orange writing on here on the top. If you have version B, it is the green writing on the bottom. So there are your formulas for the first three, ladies and gentlemen. Okay? The third one, I was a little disappointed. A lot of you had it right, but for some reason you decided to put sulfur in front of NH4. That's the positive ion. Positive ions always go first. So the NH4 should have stayed at the beginning, like the order that I gave them to you in the problem. So, but there are your three formulas. There are the three answers. Okay? Questions? Each one was worth a point. If you had the formula right, you got a point. If you had the name right, you got a point. Okay? Coming down to the bottom. One version had 64 grams of neon gas. The other one had 93.2 grams of argon gas. This is a 2-point conversion because 1 point for setting it up correctly, 1 point for using the correct formula masses. By the way, here were your formulas, ladies and gentlemen. Okay? Then you convert it into liters from moles. If you managed to do this in one step, you would have still gotten all of the credit. 3 sig figs for your final answer, and your unit should have been liters. Questions on those? We're good? Okay. All right. Up at the top, ladies and gentlemen, you were given so many formula units, and you were asked to go to grams. So, in one case, you had magnesium phosphate, in the other, you had strontium borate. Writing your formulas, formula units, 1 mole over 6.02 times 10 to the 23rd formula units in both cases. Formula mass is here. You got a point for calculating those correctly, and then a point for setting it up correctly. 3 sig figs in your answers in the unit of grams. Questions? Okay. Down at the bottom, you were given a volume of a gas at STP. Here's the good news. If STP bothered you, we're done with it. Because the next unit, nothing's going to be at STP. Okay? So, 101.3 kPa and 273 is just telling you at STP. Take your volume, convert it into moles using 22.4 liters. Go to formula units from there. And the final step, ladies and gentlemen, you had to go atoms to formula unit. This compound has 8 atoms in one formula unit. This compound has 6 atoms in one formula unit. 2 points, 3 sig figs in both of these, the unit of atoms in both of these, and there were your answers, ladies and gentlemen. Questions? Okay. You wanted to find the mass of so many molecules of fluorine gas. Was fluorine gas in both problems, ladies and gentlemen? Different number of molecules, though. Same first conversion, 1 mole over 6.02 times 10 to the 23rd. Formula mass over 1 mole for the second, since these are F2 because it is a diatomic. We double the mass of fluorine, that's why it's 37.996. 3 sig figs in grams are our units there. Questions? Okay. So down at the bottom here, ladies and gentlemen, we had a compound that had different amounts of, they ended up both being the same. 28.2 grams of carbon, 1.57 grams of hydrogen, and 12.06 grams of oxygen. We take and we convert them into moles using 1 mole over the formula mass for each of these. Don't double these. These are not H2 and O2. They're a part of a compound. We get to a number of moles of each of these. We divide by the smallest mole. We got a ratio of 3 to 2 to 1. Empirical formula C3H2O. when we went to the molecular formula for sorry, I'm wondering why I have that. It was the same on both. I have 108 there. It should have been 54.6. Same molecular formula on both as well. No, actually, I'm sorry. That's what I changed on the problem. Can't be. Okay. So anyway, this one here and this one here. So I had changed this to 108 on one of the versions, and on one it was 216. That's why. Okay. So those were your formulas. Sorry to be confusing on that. Any questions? By the way, if you didn't write your final formula down, you lost the last point. You have to actually double this formula or take it times 4 in this case. So, questions? Okay. Monosodium glutamate means nothing in this problem. It's just the name of this compound, ladies and gentlemen. But this compound had 5 different things in it. Okay? Now, again, it had sodium in it, but this is an organic compound that has a metal in it. So, again, your formula should have been written in the order that I gave them to you, because that is what you are supposed to do when I give you the compounds. I don't expect you to know which one goes first in these, because this is not a simple ionic compound. Okay? So again, we take our grams of each of these, all 5, and convert them into moles using formula mass. Once we're into moles, ladies and gentlemen, we divide by the smallest amount of moles. We get a ratio of 5 to 8 to 1 to 1 to 4. So that is your formula, C5H8NNaO4. Versions A and B were the same. Questions? Okay. All right, problem number 8. Okay, 2 different compounds, calcium carbonate, sodium nitrite. Formula mass for calcium carbonate is 84.09. For sodium nitrite, it is 68.996. You take the mass of calcium, and there's only one of them, divided by the total mass, gives you 46.7%. You take the mass of sodium, there's only one of them, divided by the total, you get 33.3%. Carbon, it's 12.011 divided by the 84.09 gives you 14.3. Nitrogen is 14.007 divided by the 68.996 gives you 20.3. Here you've got 2 oxygens, so we double the 15.999 to 31.998 divided by the same total mass in all 3, 38.1%. Same thing here, you double the mass of oxygen, 46.4. Questions? All right. What 2 elements make more of what we are getting every day? Lithium and tellurium for light. Okay, your days are getting longer. Other people had some other things that were accepted, but it had to be 2 elements. With March Madness starting in, what 5 elements will be what I will be watching a lot of over break? Hydrogen, oxygen, phosphorus, and sulfur for hoops, for basketball. What 3 elements spell out what a lot of people have on spring break? Fluorine, uranium, and nitrogen for fun. And what 3 elements describe what I really need to do to my truck over spring break? Tungsten, arsenic, and hydrogen to wash it. Which I didn't, by the way. So, other answers that were reasonable were accepted. If you tried to stretch things, I maybe gave you a point. Okay? Questions? Okay. If there are any mistakes that I made, either in grading a problem, adding up your total, adding up the total that is on the front, you need to put a note on the top of your test right now, and you need to leave it on my desk before you leave class today. If you don't, I will assume that everything is okay and we are good, because if you don't have your complaint now, you don't get to take it home and figure out what it is. So, questions? since parent-teacher conferences are 2 weeks from tomorrow, ladies and gentlemen, please understand that we will have probably 1 or 2 more quizzes before then, maybe a lab in there, but basically the grade that you are looking at right now is probably the grade that'll be pretty much what is on your report card. Now, there are some exceptions to that. We will talk about those in a minute. Jesus. Hola.
That is why I knew it.
Adelaide. Madison. Linda. Daniel. Okay. Now, I want to point out a couple of things to you, ladies and gentlemen. There are a few of you who have some things to make up. Some of you did not take the test last week. We need to get it done by the end of this week. Okay? If you are missing a quiz, we need to get that done before we will take the test. Well, if it's the second one, before you'll take that test. And they both need to get done this week. So, I will be requesting some of you into my home base tomorrow and on Friday, if that is the case. If you are missing this lab, ladies and gentlemen, the new policy for science work, for late work, is we gave the test last week, Friday, or the last Friday before spring break. You get 1 week to turn this in. If it is not turned in by the 4th of this week, that is Friday, it will be a 0 and it will stay a 0. I will not accept it. Okay? I will not accept it. Now, most of you have your lab done, and that is great. But if you look on your list of things there and your lab is a 0, ladies and gentlemen, you have until Friday to get it in, no exceptions. Friday to get it in, get it turned in. Otherwise, it goes in as a 0 and it stays as a 0. By the way, right now, that is the one lab that is 20% of your grade. So without it, you are 20% down in your grade. So just so that you understand. Questions? There are not a lot of things on that list, ladies and gentlemen. There are your quizzes, your one test, and the lab. And that is the way it is going to be in this try, much like it was in the first try. So, again, if you are missing something, it is counting against you, and it is a big portion of your grade. Get it taken care of, please. Okay? Questions that you have at all about anything that we have talked about this morning? Okay. All righty then. All right. So here is our agenda for today, ladies and gentlemen. First of all, we just asked if you had any questions on the grade report or anything that has been going on. The reminder, anything that is missing is a 0 and until it gets turned in. Now, again, I will give you a little bit of time for quizzes and for tests, but your lab needs to be in by Friday. Otherwise, keep it. It's a 0. Here's our plan for today, ladies and gentlemen. This next unit is all on gases and the behavior of gases and the factors that affect gases and gases in general. Now, the last unit we introduced them. How? 22.4 liters of gas is equal to 1 mole at STP. Okay, that is gone now. That is off the table. We are no longer going to talk about gases at STP. Maybe a little bit at the start, but most of the gases that we are going to deal with in this unit will not be at STP, just so you know. So today we've got a number of things to get through in the slides and that. We will get through them. We will talk about them. I've got a few demonstrations for you for today that we will get to. And then tomorrow we'll work on doing some conversions. Again, a lot of math and things in this unit. Sorry. Thank you. So, in this unit, you again are going to need to write formulas and things. That you're going to be doing from here on out. I did do this, ladies and gentlemen, and I can give you one of these. Oh. For those of you who are still struggling a little bit with formulas, I wrote this cheat sheet up for you. It's going to be very helpful in the next 2 units. On the front side is a reminder of writing formulas. And it goes through the different types of formulas that we have written. Binary ionic, ternary ionic, binary acid, ternary acid, and binary covalent. And it tells you how to recognize certain things. It tells you, reminds you when you need to do charges, when you don't need to do charges. If a polyatomic involved, where you will find the polyatomics, what the names end in, because you are going to be going from names to formulas again in this unit and again in unit 7. Okay? So the front side is a reminder of how to do some of that. Now, you cannot use this on a test unless you take and copy it onto your periodic table or your solubility chart. This is to help you when you are doing problems. The more you practice with this, the better you should get. On the back side, ladies and gentlemen, are single and double replacement reactions. Now, we will not get into a lot of these in this unit, but in the next unit we will. And it reminds you of how to balance an equation, what a single replacement reaction is, what a double replacement reaction is, what we need to look for in each of those. So I made this up for you, ladies and gentlemen, to help you. I would put it with your periodic table and your solubility chart for now. And if you're good with writing names and formulas, you can bury this in your notebook and not take it out again. I don't care. If you want to use it during class time, you are welcome to. If you don't, that is up to you. Okay? But almost everything you need to know about writing and balancing formulas and equations is on there for you. Okay. So, ladies and gentlemen, let's take a look at our EISN. So if you go into Canvas, you will find that I have posted 3 things for you again already. The Unit 6 Student EISN, the Master EISN, and the answer keys for you. So with that in mind, I might as well do this too. Take some, pass them back. When you guys are done, you could set them, you could hand them back to the front for me, the extra ones, and I will just get them back from who's ever in the front. So if I'm short in an area, let me know, and I will send more there. All right. So the answer keys for these are online for you. All right. So let's talk about gas loss, ladies and gentlemen. That is what Unit 6 is all about. It's about gases and what are called gas laws. Okay? And gas laws determine how a gas will react under certain conditions. Okay? Now, the nice part about gas laws is gas laws are very predictable, meaning gases will behave the way they are supposed to unless they are under some very extreme conditions, which we will not put them under. Okay? So, we're going to quickly review what gases are. We're going to talk about factors that affect gases. We are then going to talk about pressure, We're going to talk about temperature, STP, and conversions. We're then going to start getting into gas laws. And there are 4 gas laws, as well as a combined gas law, an ideal gas law, and then some special gas relationships. And all of these involve solving problems involving math. Predicting what a new volume will be if you change a pressure. Predicting how fast the gas will move. Predicting what the temperature of gas will be at if you change its volume. Okay? So that is what all of this is about. Boyle's, Charles Gay-Lussac's, Avogadro's combined ideal gas laws and these special gas relationships. Okay? So we're going to be doing a lot of that in this unit. We are going to be doing a lot of rearranging mathematical formulas. Solving for a variable that is being multiplied by something that is equal to 2 or 3 things on the other side of an equation. Okay? So, again, a lot of different formulas and things. Now, what I will tell you is, on the test, I will give you all of the formulas that you need. Not expecting you to memorize them. But I do expect you to know which one you need to use. So I'm going to make a suggestion to you. We are going to create a unit key on your periodic table or on your solubility chart. By that, what I mean is you need to recognize what a number is telling you. And if the number has a unit of seconds, what is it telling you? What is it measuring? It's measuring time. Seconds only measures time. Okay? If your unit measures in grams, it's telling you mass. So, to help yourself in this unit, you need to understand that when you look at a number and you see a unit, what is that unit telling you? What is that unit describing? So we're going to create a little key for you that will hopefully help you with this, ladies and gentlemen. Okay? Now, a little quick review of gases. You learned this when you were a freshman. You probably learned this even before you were a freshman. There are 4 states of matter, but one that we never talk about. We never talk about what is called plasma. It is a 4th state of matter. And to be honest, there are some scientists who believe there is a 5th, possibly even 6th state of matter. We're not getting into that. We're going to keep it very simple. And to keep it simple, solids, liquids, and gases. Okay? Now, the air that we are breathing in this room is a gas. Why? Why is it a gas? We can't see it. No. That is true that we can't see it, but that's not why it is a gas. No. That is what it does as a gas, though. Why is the oxygen that we are breathing a gas? Why is this water not a gas? Why is that pipe not a gas? I understand it is a solid. I understand this is a liquid, but you're not answering my question. Can water become a gas?
Yes.
Okay, so why isn't it a gas? What about them? Okay, that does have something to do with it, how fast the particles are moving. What about the temperature? Thank you. This water is a liquid because it has a boiling point that is higher than the temperature of the room right now. So the room is not warm enough to boil that water. The room is not warm enough to melt this pipe. Can this pipe melt? Yes, we get it up to about 2,800 degrees. This pipe will melt. Could it become a gas? Yes. About 3,600, 3,700 degrees, the iron particles can become a gas or can go into the gaseous state. So I will ask again, why is the oxygen and nitrogen and carbon monoxide and carbon dioxide and hydrogen and helium a gas? What about it? What do we know about the temperature for those things?
It's not low enough to be.
Well, what state would normally be right below a gas? A liquid. Or we could say that this room temperature is hot enough that the oxygen, nitrogen, and other gases in the air have already, not evaporated, starts with a B, ends with an oiled. Boiled. They have already exceeded their boiling point and therefore they are in the gaseous state. So please understand, most matter can be a solid, can be a liquid, can be a gas. The reason it is in one of those three is because it is either not yet melted, meaning it is a solid, it has not yet boiled, meaning it is a liquid, or it has already boiled, meaning that it is a gas. And that all depends on the temperature. Now, there are some substances that will not melt. Will wood melt? No. Instead, if we add too much energy to it, it will combust. It will burn. It will chemically break down what it is and change into something different. Okay? Certain substances do that. They cannot melt. They cannot boil. But most can. Most have a melting point. Most have a boiling point. Okay? Now, people always ask, well, what would happen if it got really, really cold outside? Would we die from the cold? Well, we probably would die from the cold, but we would die from the lack of oxygen in the air first. Because if it ever got cold enough that the oxygen in the air liquefied at about minus 208 degrees Celsius, there would be nothing in the air for us to breathe when we walk outside because there would be puddles of oxygen as a liquid laying on the ground. And when that's the case, you and I have nothing to breathe. We would have to somehow find a way to warm that up and get that back into our atmosphere. Otherwise, we have nothing to support life. Okay? Now, if it ever gets that cold, we're probably in trouble anyway, ladies and gentlemen. Okay? But all those things you were telling me about a gas are very true. Gases are unique because they have no definite shape and no definite volume. Gases take the shape of whatever container you put them in, and they completely fill the container that you put them in. You do not walk into the corner in the back of the room and start choking to death because there is no air back there. It is everywhere. And it's a good thing that that happens because you and I can't see these gases, so we wouldn't know what area to avoid where there is no gas to where we would start dying from it. But gases completely fill whatever container they are in. The largest container, basically the atmosphere around us, the Earth. What is stopping the gases from going off into space? Gravity. Gravity stops the gases from going off into space. Are there a few molecules that escape? Absolutely. Are there a few that come back from space into our atmosphere? Absolutely. But the number of particles in space is sparse compared to what is in our atmosphere. Okay? Now, gases have the most energy out of all three of these states. The gas particles are moving the fastest. Okay? They have high energy. In a solid, particles just vibrate back and forth. In a liquid, they move a little faster. They can slide past one another. Gases are moving with enough energy that they get completely free of each other and far away. In a solid, in a liquid, there are these things called forces of attraction. Kind of like the force that is holding this magnet in place here. There is a force that holds this magnet to the metal door frame. It's called magnetism. Okay? What keeps us on the Earth's surface? Gravity. Right? So you can jump up, you're coming back down because of gravity. That is a force of attraction. Magnetism is a force of attraction. In any solid, there is a force of attraction that is holding the particles together. Even in a liquid, there is a force of attraction that holds the particles together. But in a gas, they get spread out. And it's not that those forces of attraction don't exist. But if I take this magnet far enough away from the door frame and I release it, what happens? Why? Good. Exactly. The strongest force wins. And the force of gravity out here is stronger than the force of attraction between these two. Now, please understand this too. When I take this away from the frame, people are like, I'll ask, well, what happens to the magnetism? Well, it shuts off. No, it doesn't. The magnetism never shuts off. This is always magnetic to here. The problem is the distance between them is so great that other forces get in the way. The force of gravity pulling it down. Okay? Now, if I hold this close and release it, it will go to the frame. Force of attraction is strong enough to pull them together. Stronger than the force of gravity pulling it down. Strongest force always wins. Well, the particles in a gas are far away from each other. So even though there is a force of attraction by being far away, they don't feel it. They don't feel it. And here's the other thing. Do particles of a gas ever hit each other? All the time. This room is full of particles of a gas. They are hitting each other. They are hitting you right now. Do we feel it?
No.
No, because we've lived with it since the day we've been born. Leave your phone. Gas particles right now are bouncing off your head. They're bouncing off the walls. They're moving in every direction, hitting each other. So, okay, well, if they hit each other, they're no longer far apart, are they? And far apart was the reason they don't attract. So how come if they hit each other, they don't stick together? Why don't they stick together if they hit each other? Think about how they're moving. How are the particles in a gas moving? What? Really fast. So they hit each other, why don't they stick together? They bounce off. When they hit each other, they get a chance to attract each other and stick together. The problem is they're moving so fast that when they hit each other, they bounce off before they get a chance to attract to each other. So how do you take and make a liquid or a gas into a liquid? Why? Agreed. But what does slowing down the particles do then? When they hit each other, if they're not moving fast, they don't bounce off of each other. Now all of a sudden they start to stick together. They make a liquid. How do we make a liquid into a gas? What? What does heating it up do? Increases the energy, making the particles what? Move faster. So now, even though they're stuck together, they're starting to move faster. Well, they're hitting each other, moving faster until eventually, boom, they can get free of each other. That's the unique thing about gases. That is the unique thing about gases. All right. So, we need to go back and we need to talk about something we have already covered. Why? In gas laws, we are going to talk a lot about the mathematics, but we're also going to talk about the relationships. And the relationships that I want to talk about are a direct relationship. That is where one variable changes, the other variable goes in the same direction. Okay? If you walk up to a bubbler in our school and you want a bigger drink of water, what do? If you go up to a bubbler and you want a big drink of water, what do? How do you get more water? Come on, this is not a hard question, guys. You've gone up to bubblers in our school. If you want more water, how do you get it? What? Hold the button down longer. You increase the time you're holding the button, what happens to the amount of water? That is a direct relationship. That is a direct relationship. The longer you hold the button down, the more water you're going to get. Okay? If you put a pot of water on the stove, what does its temperature do? It increases. How can you make it increase more? Turning up the heat or leaving it on there longer. The longer you leave it on there, the higher the temperature is going to get. Both direct relationships. A direct relationship says if one thing is going up, so will the other. Mathematically, your two variables get divided. If you have one variable divided by another, that is a direct relationship. If the variables are divided in your mathematic formula, this is a direct relationship. Okay? So speed is equal to distance divided by time. The more distance you cover divided by time, the greater your speed. Okay? An inverse relationship is a relationship where if one variable goes up, the other goes down. One variable goes up, the other goes down. The amount of time you spend working at your job increases. What happens to the amount of free time you have? That is an inverse relationship. That is an inverse relationship. The more time you spend working, the less time you have to do other things. Inverse relationship, ladies and gentlemen. Mathematically, what would you do to your variables? You would multiply them. You would do the opposite that you would do in a direct relationship. If you are dividing your variables in a direct relationship, you are going to multiply them in an inverse. Okay? And if you have a larger amount of water and you want to create the same temperature change, you need to add more energy. Okay? Add more energy. Inverse relationship. One going up, one going down. Okay. A constant relationship means what? What does a constant relationship mean? No. No, but you're close. Constant relationship means your variables are changing at the same rate. One thing is going up, so is the other, but they're going up at the same rate. Hence, when you look at a graph, you would get a what kind of line? Straight line. Straight line. By the way, is that a direct or an inverse relationship? That graph. Direct or inverse? Why direct? Because the line is going up. Any line that is going up on a graph is a direct relationship. If the line is straight, it is constant. Okay? If it is straight, it is constant. Is this a constant relationship? Why? Okay. But it's no longer what? What is it? This is an inverse. Inverse goes down, direct goes up. Constant means it's straight. Non-constant relationship, one variable changes, the other changes at a different rate. How would you recognize that in a graph? The line is curved. The line is curved. Now, this is still a what relationship down there? That is still a direct. Why? Because the line is going up. Line going up, direct. Straight line constant, curved line non-constant. Okay? Which way is the line going here? Really? Still going up, which means it's still what? But it's also non-constant because the line is curved. So, the direction of the line, direct or inverse. The shape of the line, straight or not, constant, non-constant. And I will not give you any lines that try to fool you. If the line looks straight, it's supposed to be straight. If it looks curved, it's supposed to be curved. Okay? All right. So again, graphs are straight line constant, graphs are curved line for non-constant. Wonderful. Okay. The one gas that is all around us, ladies and gentlemen, is air, which is a good thing for us, but it also does other things. Okay? So, air is a homogeneous mixture of gases. Quickly, what does homogeneous mean? No, mixture means mixture. Homogeneous means what? No, otherwise it wouldn't be a mixture. There's homogeneous and there is heterogeneous. Homo means same. What is the same? A mixture of gases, meaning it is the same throughout no matter where you go. The air that we are breathing here is the same as the air that they are breathing on the other side of the earth. The same combination of gases, the same basic things involved. And homogeneous means that they are evenly spread out. Okay? The mixture is the same no matter where you go. Heterogeneous, the mixture is different. Homogeneous, the mixture is the same. So it is evenly distributed and has a definite ratio. That is the air that we are breathing. Now granted, some areas there will be slight differences in air, pollution, air quality, things like that. But most of the air you would breathe, no matter where you go on the earth, is the same exact thing. The same exact thing. Okay? And it is made up of various components. What is the major ingredient, the most of the air we are breathing made up of? Nitrogen. 78% of the air that we are breathing, ladies and gentlemen, is nitrogen. Do we need it? Absolutely not. We take it in, we breathe it, we exhale it, we don't need it. It doesn't do anything for us at all. However, the other 21% oxygen does. Supports and sustains life on this planet. Okay? Interesting fact. It's a good thing that's not a few percent less. We would lose much of our population. Anyone who has any breathing issues, emphysema, lung cancer, certain allergies that cause difficulty breathing, they would die because there'd be not enough oxygen in the air. But if we went a few percent higher, it would be a bad thing for us because we would never stop a fire. The environment would be too oxygen rich. We would have a hard time putting out fires. And I'm not talking about just like the wildfires that spread in other areas. We're talking about a house fire. We're talking about turning off the, anything that is burning, a fire in your fireplace, things like that. As long as you would give it the wood or the material that it is burning, it would keep burning, and it would be very difficult to put out with a too oxygen-rich environment. This is why they will not let people smoke in hospitals, because of all the oxygen that is there. And then it's about 1% other gases. Carbon monoxide, carbon dioxide, water vapor in the air, all of those things. Okay? All right. There are 4 factors that affect the gas, and this is the major part of this unit, ladies and gentlemen. There are 4 things that affect the gas. So here is number 1. Number 1 is pressure. Pressure affects gases. You can put gases under more pressure, you can put them under less pressure. Pressure is the amount of force applied to a certain area. That is what pressure is. That is the definition of pressure. The amount of force applied to a certain area. Second factor is volume. Someone tell me what volume is. What is the definition of the volume of something? Volume is the amount of space an object occupies. Every substance occupies a certain amount of space. Now, the unique thing about gases is that its volume can change. The volume of this tabletop up here cannot change. It doesn't get bigger, it doesn't get smaller. Maybe a tiny bit due to temperature. But gases, you can release a small amount of gas in this room and it will take up the entire container you give it to. Gases spread out evenly. Gases take up whatever container you will give them to. If we have a helium balloon and we pop it, that helium will spread out throughout this entire container. Throughout the entire container. Gases' volumes can change dramatically. Number 3, ladies and gentlemen, is temperature. Okay, you already know what the definition of temperature is. Tell me what the definition of temperature is from the last trimester. It's a terrible thing when you're supposed to remember things, huh? Anybody? Temperature is the average kinetic energy in the particles of matter. The average kinetic energy in the particles of matter. Okay, so we sucked at that definition. Let's see if we can do this. What does kinetic energy depend on? What does the kinetic energy of an object depend on? What 2 things? The object's what and what? What? So its energy depends on its energy. Think about that. Mass is one, and the velocity or speed is the other. Now I want you to think about something for a minute. The air particles in this room, the oxygen particles, the part that we are breathing, what can't we change about those particles? The mass. The particle mass is determined by what the particle is, correct? We cannot change that. So what is the only way to change the temperature of a gas? Make the particles change speed. So in reality, when you are talking about the temperature of a gas, you are talking about how fast the particles are moving. That is the only way to change their temperature, is to make them move faster or make them move slower. Because you cannot change their mass. Okay? You cannot change their mass. By the way, in this unit, we are going to have to convert temperatures into Kelvin. Kelvin is the 3rd system for measuring temperature. Celsius, Fahrenheit, and Kelvin. Okay? Anybody know what's unique about the Kelvin system?
Nope.
Obviously. Your physical science teachers did a wonderful job with you, including me for some of you. What? It is what is called an absolute scale, meaning the lowest temperature possible is 0 Kelvin. You cannot have negative numbers. We'll explain why that's important in just a second. The 4th factor that affects a gas is how much gas there actually is there. And that we measured in moles, that we figured out in the last unit. If we knew the volume of a gas, we could figure out how many moles there were. Okay? If we knew the moles, we could figure out the volume the gas would occupy. Now, the problem is other factors can change. Jade, what is the least amount of pressure you could apply to an object? The lowest amount of pressure you could ever have. Take a guess. What do you think the lowest amount of pressure pushing on something could ever be? Let me re-ask the question. If pressure is applying a force against something, is there a way to have a negative pressure? So what's the lowest amount of pressure you could ever have? Which would make how much pressure? Zero. Thank you. Zero. Zero is the lowest pressure you could ever have. Elsa, what is the least amount of space something could ever occupy? None. You cannot occupy a negative amount of space, correct? So you cannot have anything lower than zero pressure. You cannot have anything lower than zero volume. What is the least amount of gas you could ever have? What is the least amount of gas you could ever have, Linda? None. Zero. So for amount of gas, for volume, and for pressure, the smallest you could ever have is how much? Zero. Why do we need to use Kelvin for temperature? What? Because it's also an absolute scale, meaning we cannot have a negative temperature. If we are going to talk about relationships between these four things, we can't have any of them be negative, because three of them can't be negative. There is no way you can have a negative pressure, negative volume, or negative amount of gas. So we needed a temperature scale where you'd have no negative numbers either. That is the Kelvin scale. That is the Kelvin scale. Okay? All right. So here's the first thing that you should do, and you should put this somewhere on your periodic table, somewhere on your pink sheet, somewhere on something that you can look at on a test. There are four basic units for pressure that I will give you, ladies and gentlemen. Four different units for pressure. And they are mmHg, millimeters of mercury. They are ATM, or atmospheres. They are PSI, for pounds per square inch. And they are KPa, or kilopascal. Those are the four basic units. Now, these are not the only four units, but these are the four most common units that we will use in this unit when we are describing a pressure of something. It will be either in millimeters of mercury, ATM, PSI, or atmospheres. So if you see a number with any one of those four units, that number is describing the pressure of something. Volume, there are three basic units. Now, the most common one will be liters, but we could also talk about milliliters and cubic centimeters. And this may be an important thing you wish to write down as well. A milliliter and a cubic centimeter are the same thing, ladies and gentlemen. 1 milliliter and 1 cubic centimeter are exactly the same amount of volume. Temperature, you may be given it in degrees Celsius. Many times we're going to have to convert it to Kelvin. Okay? So most of the time when I give you temperature in a problem, it will be in degrees Celsius. You will have to convert it into Kelvin. We will show you how to do that tomorrow. I will never give you a temperature in Fahrenheit. You should never collect the temperature in here in Fahrenheit. Celsius is the temperature that we would use with our thermometers. We can easily convert that into Kelvin. And finally, amount of gas, what unit would it be in? What? In mole, which, by the way, what could also easily be mole be changed into? In the entire last unit. What? Nope. Could be, won't be. What's the other one? You've given me volume, you've given me particles. Mass. Mass you will get. You will get the mass of a gas, and you will have to convert it into moles. All right? You will get the mass of a gas, and you will have to put it into moles. Okay. Close your computers, please, once you have this copied. Claire, can you volunteer to help me with something? Come right up front here, Claire. Okay? What did we say pressure was? The amount of what? Force applied to a certain what? Well, the best demonstration for this, ladies and gentlemen, is right here. And Claire is going to help me with a bed of nails. You willing?
Sure.
Okay, good. So, Claire, what I want you to do is kind of stand over by that empty desk by Linda for now. Okay? All right. So here we go, Claire. You get an easy job. You're going to stand on the bed of nails. Okay? So, let me get ready. And you are going to stand on the bed of nails. Now, whoa.
All right.
Can we slow down a little bit here? You seem very excited to get on the bed of nails. Use this and Linda's desk to steady yourself. Please try not to rock back and forth so the nails don't dig into my flesh too much. Okay? And I have one major rule.
Yes.
No jumping.
All right.
Okay? Are you ready?
Yeah.
Okay, give me just a second. All right, Claire, let's do this.
You sure?
No, but let's do it anyway. Okay, here we go. Here we go.
Ugh.
Okay, you're rocking.
I know I am. I
know.
can feel it.
You're okay.
Stop breathing. You're moving.
Stop breathing. It is my fault that she's rocking. Okay, use this and this to spread your feet a little wider. There you go. Get up on your base. There you go. Why is it she seems like she's having the harder time in this demonstration, ladies and gentlemen? Are you okay?
Yeah, I'm great.
Okay.
Are you
Could
good?
you I'm actually pretty good here.
Okay.
Okay, could you get off for a second?
Yeah.
Okay. All right. So now we need to change things, ladies and gentlemen. Okay? Now, what are the two factors, excuse me, Claire, for a second. What are the two factors that can affect pressure? No, not mass. Gonna have more what? No, pressure is, what is the definition of pressure? The amount of applied to an area. So where in there do you hear mass? What? Good. Jesus, can you come up and help us here? Come here. Okay. Claire, move out of the way just a little bit. Okay. This time, Claire and Jesus are going to stand on the bed of nails at the same time. Okay? All right. Now, just hang on a minute here. Okay. So one of you here. You got to get on at about the same time. Okay? And whatever you do, no jumping. I'm looking right at you. Trying to get a nice wide base. All right. Okay. All right. I think I'm ready. All right. Holy cow, it's like they're really light. Oh, wait, they're not on yet. Okay. All right, go ahead. Okay. Oh, my goodness.
He's trying.
I am not crying. This is actually not bad. Clip, you can let go of the table if you. Holy cow. Okay, you guys are rocking. You're rocking. Can you stand still? Okay, good. Excellent. All right. Now, please get off. Good. Good. Wait a minute, you're not done yet.
Why?
You're not done yet. What? There's not room for three. Forget about it. Forget about
I
it.
mean, if you carry somebody.
Madison, you want to be the third person in here?
Sure.
Okay, come on up. Madison, I'm glad you volunteered. Okay. Actually, Jesus, you can sit down. We'll start with just clarify. Go ahead and lay down, Madison.
Oh.
You said you wanted to be a part of this. Go ahead and lay down.
No.
Lay down on the floor. Okay. Relax. We'll start with just Claire. Okay. But the bed of nails is kind of scary, isn't it?
Well, I didn't think I'd
Okay.
be doing this.
I know it's kind of scary. So we'll let you begin with the starter kit.
Gee, thanks.
Here's the starter kit, ladies and gentlemen.
What's the?
Lay down.
No.
Lay down.
No.
Lay down. Okay.
No.
Hold this about right there. All right. So Claire, you're gonna step on that.
Sure, if you kill me, I swear to God, I will not even laugh. Okay.
Yeah, I didn't get that. You really want her to stand on it?
No.
Why?
Oh,
What did we
I like
change?
it.
She would have the same force she had when she stood on me, and I stood there and I took it. Didn't complain one
But
bit.
listen, Linda, we have one spike going into me, whereas you have like a bunch of.
So what did we change?
We changed the.
What did we change?
Can I get up there?
The what? Yes. Thank you. Okay. We changed the area. What did specifically we do to the area with only one spike? Reduced it. Okay? So, now, let's talk about this. When we had Jesus and Claire both on the bed of nails, what did we change? The force. And it went how? Up or down? Only two ways it can go. It went up. Okay? It went up. So what happened to the amount of pressure that I felt underneath it? It did increase. It did increase. It was more difficult with the two of them standing on the bed of nails than just one. Absolutely. Now, here we're changing the what? From here to here. We're changing the area. Claire would have provided the same force on this one nail that she provided on the bed of nails. However, one nail would have gone right through Madison. We would have needed a hammer to get the nail out of the floor and then remove her body afterwards.
I don't think that's how that works.
Okay? You don't think it would go through down into the floor?
No. Maybe like, well, maybe a little bit.
A little bit, right through you. Now, what it also means, ladies and gentlemen, is that you can take
Wait.
and stand on a bed of nails.
Oh yeah.
Because you're standing on what? A greater area. But if you've ever walked and stepped on a board that has one nail sticking out of it, what happens to the nail? It goes right through your shoe and into your foot. Okay? Why? Because it's all about force and area. Now I've got a big enough area over which my force is spread out so that it doesn't go through my shoes and into my feet. If I was standing on one nail, I would impale myself. Okay? I would impale myself. Alright? Now, gases feel pressure and exert pressure, and that's what we are going to talk about with them tomorrow, ladies and gentlemen. You know, I don't hear Claire complaining about standing on top of this. You really shouldn't complain about being under it. I mean, Claire was willing to take one for the team. She was.
Oh, you were about to do it, Claire? I'm sorry, you couldn't.
No, Claire never volunteered for that. You wanted to be the third person, so.
Well, I didn't think I was positioned.
Well, just stop your statement with, I didn't think. Okay? That would be good enough. Okay? That would be good enough.
Because you're being very rude. Don't give me this.
Don't give you what?
Oh, no.
I can still bring you up here. We can do the demonstration real quick.
No,